Waiting on anybody? All right, so let's go ahead and get back into it. So, are there any questions before we start about anything? Okay, so we talked about saddle point bounds last time. So we left off with Pn is P of n is less than q to the minus n times the whole generating function. And the goal was to try and optimize this. Bounds on the right hand side. Yeah, and I guess I should say that's for q positive number, less than 1. And so it turns out that this guy here is a concave up function, or convex if you like. So like so. And so it has a unique minimum here. So unique minimum Q naught that satisfies the saddle point equation. What was it? Q naught times the logarithmic derivative equals n. So that's where the unique minimum there occurs. So yeah, so let's go ahead and try and solve this, or solve it approximately. So we're not going to be able to write down, something simple for Q naught in this case, but we can approximate it. So let's go ahead and do that. All right, and all right. So let's compute Q times this. So that's the derivative of the logarithm of this guy. All right. So it's going to be a lot of computation today. And it's the log of this product. And when you take the log of the product, you can pull out the product as a sum. So I get something like that. And let's keep going using the Taylor series for the logarithm. So this is a useful Taylor series that comes up all the time. So I'll write it up here. This guy here, his Taylor series is x plus x squared over 2 plus x cubed over 3, and so on. So I'll go ahead and use that. You need the minus sign here in front. So I'll get q, let's see, I need another sum. Sum over m, q to the km over m. And everything's absolutely convergent, and I can swap the sums. And I'm going to now sum this over k. And this is a geometric series when you sum it over k, right? So this is going to be q to the m over m times 1 minus q to the m. Okay? And then, as I say, everything's absolutely convergent. We can swap the derivative in the sum and take the derivative. And I'll just tell you what you get when you do that. So you end up with q to the let's see, why am I? Yeah, no, it's okay, I think. Okay, so you end up with q to the 2m over m. Oh yeah, okay, that's why. This goes away when you take the derivative. Okay, so I think you end up with that when you take the derivative. So we want to solve the equation this equals n, or approximately solve it. So we want n equals this. And this is where I'm going to kind of wave my hands a little bit with this. So I'm going to, first of all, pull out a factor of 1 minus q from each of these. 2 of them because it's squared. So then I'm left with something that looks like this. All right. Okay. And so we want to solve this, and the solution to that is our saddle point. And really, I just want the approximate solution as n tends to infinity. So here, the left-hand side tends to infinity, obviously, as n tends to infinity. And so my solution to this equation, whatever it is, the right-hand side also needs to tend to infinity. Yeah? Good.
Can we go through how we take the derivative, because I keep getting q to m, not q to 2m?
Yeah, that might be wrong. Yeah, I think you might be right. Let's see. Yeah, okay. Yeah, I think it is q to the m. Actually, it doesn't matter, but yeah. Thank you for pointing that out. Yeah, I think that's q to the m. Okay. Okay. So the left-hand side tends to infinity, as n tends to infinity, obviously. And so what needs to happen for the right-hand side to tend to infinity is that q needs to tend to 1. So all I'm trying to say is that our saddle point, whatever it is, has to tend to 1, so that this guy tends to infinity. Okay? So this means that our saddle point q naught needs to tend to 1 as n tends to infinity. And so if it tends to 1, well, this guy here, as q tends to 1, is going to be approximately 1 over, I have m here in the denominator, 1 over m squared. And so this guy, as q tends to 1, is going to be approximately the sum of the reciprocals of the squares. That's pi squared over 6. So we want to solve this equation. And this is pi squared over 6. So pi squared over 6. Okay. And here we can work out what q has to be by just doing some algebra. And a convenient choice of q. So well, yeah, maybe I'll do the algebra. Okay, so we're going to get that 1 minus q has to be pi squared over 6n, well, in the square root, so pi over root 6n. And so, you know, you can make q 1 minus that, but actually a more convenient choice is the following. And this is the choice that you'll see in all the literature for this, is e to the negative pi over root 6n. Okay, so this is going to be our approximate saddle point. That's for Q, yeah. So this is your Q naught saddle point, yeah. Okay, so yeah, the saddle point is approximately this. Maybe there's a Q naught that does a little better than this, and you want to be more precise with this approximation here and get a better saddle point. But you know, we can plug in any Q naught we pick here into this saddle point bound and work out what it is. And this is a convenient choice. And all right. So now what we want to do is just take this Q naught and plug it into the right-hand side of the saddle point bound, and then work out how that behaves. Okay, so P of n is less than, I'm just plugging in, e to the minus pi root n, or let's see, positive, pi root n over root 6 times p of this guy. Right? And then we want to understand how this grows. And then we'll have a bound for P of n. Okay. Now, it's always easier when you're dealing with products to take logarithms and deal with sums instead. So instead of studying this guy, I'm going to take its log and study that. And then we'll exponentiate. Okay, so this guy so it's the log of a product. We have, so actually I think I can just go ahead and plug into this right here. So that's just working out the partition function. So let me just use that formula I have over there again. Yeah, m. So, do I want to use that one? No, I don't want to use that one. I want to use, sorry about that. I want to use this one. All right. So, we have so that equals that just by taking the logarithm of the product. And now I want to think about this guy. So when you have a sum like this, and so it's an infinite sum, and you have some parameter here that's tending to 0 as n tends to infinity. And so this is kind of like a Riemann sum, actually. So this is, so we want to make this into a Riemann sum for the integral of this function. So minus log 1 minus e to the minus u. So that's how we're going to try and think about this. Okay, so to make it into a Riemann sum, I need to introduce what becomes the du, your sort of delta x in the calculus sense. So here I need to introduce a pi over root 6n, and then let me write that in red. And then I'll write that over here as well. So now what we have is a legit Riemann sum for this guy. And if you look at the graph of this will be from 0 to infinity. What kind of function is this? Well, it's a decreasing function. And so this Riemann sum is going to be strictly less than the integral, because we're taking right endpoints there. So I can bound the Riemann sum from above by the integral, and the integral we're going to be able to evaluate. So we get that the log of this guy is less than this times the integral from 0 to infinity of minus log 1 minus e to the minus u du. And this you can evaluate. It's pi squared over 6. So what we end up with there is pi root n over root 6. And so plugging into what I have there. Okay, so that's an inequality for the log. So that means that this guy would be less than the exponential of this. And then the partition function has to be less than the exponential of, well, this plus this. So twice that. And if you rearrange, you get that right there. So P of n is strictly less than the exponential of pi times root 2n over 3. And that's in fact the correct exponential order for P of n. So in fact, so remember, P of n is asymptotic to 1 over some constant divided by n, and then this exponential here. So we already have this from the asymptotic formula just by this simple calculus stuff, right? Like all I've done besides some hand waving here is just calculus. So these saddle point bounds are are really powerful. Yeah, so we've shown let me restate this in logs. We've shown that log Pn is less than this, and I'll just comment that you can get the reverse inequality of this as well. And I won't carry out these details, but we can also get that log Pn is greater than the same guy plus something of smaller order. Using these elementary saddle point bounds. And I'll give you a reference for that. It's probably in lots of different places, but here's one place that I saw it. So it's in Petrov. Two elementary approaches to limit shapes from 2010. So these saddle point bounds give you the correct exponential order. And that's generally the case with these sort of partition generating functions. Any questions about anything? Okay, great. Maybe I'll keep this. Oh, no. Okay, so for the people who don't care at all about analysis, I want to give you a fun combinatorial problem. So we proved that, so here's a fun problem for you, homework. We showed that this equals something like q to the m over m times 1 minus q to the m. So show that this implies kind of a fun recurrence for p of n. N p of n equals the sum from j from 1 to n of p of n minus j times sigma j, where this is a function coming up in analytic number theory or multiplicative number theory. So this is the sum of divisors function, where sigma j, or let me say sigma n, is the sum of all the divisors of n. That follows from this formula. So see if you can prove that. To me, kind of a surprising recurrence that connects the partitions to these divisor sums. Yes?
I have one more question. Is it the sum or the derivative of the sum?
You mean here or?
No, up there.
I think it's this. Or no. Oh, okay. Yeah, because that's from the derivative. Yeah, so maybe it's this? Okay, thank you. Sorry about that. Okay. So we want to improve this saddle point bound idea, and that's where complex analysis comes in. So Cauchy's integral formula So you can think of this as repairing the inequality. So this repairs this to an equality so P of n equals 1 over 2 pi I times the integral over a circle of the generating function divided by, so I'm going to write it this way, q to the n, and then dq over q. And I want to write it that way because if we, okay, well, so this is the integral over some circle, positively oriented, sitting inside the unit disk because, right, this guy is holomorphic inside the unit disk, and so I gotta choose a contour that's inside the unit disk. And if I make the change of variables here, so I'll want to, I'll draw some pictures in a minute, but I'll want to trace my contour through the saddle point Q naught. And so what is this contour? This contour is going to be Q equals Q naught, that's the modulus, and then the phase is e to the 2 pi I theta, right? So I'm going to make this substitution, and now this integral is the integral, I'll write it this way, from minus 1/2 to 1/2 of P of Q over Q to the n d theta. So where Q is this. Okay? And so now we see immediately the saddle point bound, right? Just slap absolute values on this, pull them inside, that's the saddle point bound. So we want to somehow improve the saddle point bound using this integral. Okay, so now some general remarks on absolute values of holomorphic functions. So if A of q, this generic generating function I wrote down yesterday, is holomorphic, in, let's say, how do I say this? Well, it doesn't really matter where, but in its radius of convergence in a disk. And we'll say that ANs are non-negative. Okay. Then this, if I look at this surface here, the modulus of this holomorphic function, this has no local mins or local maxes except where it equals 0. So that means that every place the derivative equals 0 isn't a local min or a max, so it's a saddle point. So, you know, I've been using the word saddle point, but this justifies why I've been using the word saddle point, because this thing that satisfies this equation is a literal saddle point of this surface. So, Q naught, as above, is a literal saddle point of this surface. And now I'm going to draw some horrible pictures for you. I'm going to do my best. So I want us to think about the integrand, well, the surface of the integrand here. So the modulus of the integrand, mapping it in 3 dimensions. What's going on there? So yeah, this is going to be really hard to draw, but so here's the real axis, and here's the imaginary axis, and the complex plane is right here, down in the bottom. And our Q naught, our saddle point, is here, and this is the parabola that I've translated from here. But now we're thinking about the rest of this, and we're tracing our contour through here. So we have some contour, and yeah, the surface of this looks something like this. I'm sure there's some better artists here, but that's the idea. And so we want to think about how we're going to analyze this integral. And what's going to happen as n tends to infinity is that this portion around the saddle point here is going to grow more and more and more. And the behavior next to Q naught is going to dominate. And the rest of this over here is not as high as the stuff over here. That doesn't contribute as much as the stuff over here. So I'm going to have some portion here near Q naught. Maybe I'll redraw the circle here as well. And here's the unit disk. So the blue portion is going to dominate as n tends to infinity, and the rest of this is going to be negligible. So in the literature, we call the blue part the major arc, and it is what's going to dominate as n tends to infinity, And then we have a minor arc. Which, will not dominate. Will be dominated by the major arc. So negligible. It might still contribute, it's just that the major arc contributes more and beats it out. Okay. So there's several things going on. We have a Q naught that we've chosen that is our saddle point, and as n tends to infinity, Q naught in the partition's case is tending to 1. So Q naught tends to 1. So the radius of the circle of integration is growing. It's getting bigger. And, well, we're going to, so this blue portion, which is the major arc, as things grow, this portion that we're going to consider the major arc is going to shrink as well. So it's going to become more and more peaked here. And this part here, I'll call this angle theta naught. And it's going to shrink that way. So two things are happening. The major arc is going to become smaller and smaller, and the circle, the radius of the circle, is going to become larger and larger out to 1. Okay? So the major arc will be let's see, where can I draw this? So this will be our major arc. And then the rest will be the minor arc. All right, anybody confused? Any questions? Okay. So I want to say one more thing before we get into an example, and I'm not going to do the partition function today. Sorry to disappoint you. I'm going to do an easier example. But I want to say one more thing about the major arc, and that is that, so let me draw another picture of this from the side. So if you imagine sitting at the origin and looking to your right, you would see something like this. And so what we're going to want to get for this guy is going to be of the form e to the minus x squared. Our goal for the major arc is to get something like this, because then we'll wind up with a Gaussian integral that we can evaluate. Okay. All right. Oh, and I should have said, this method that I'm describing is called the saddle point method, or sometimes it's called Wright's circle method. So E.M. Wright was the co-author with Hardy of this famous old textbook on number theory. And he did a lot of asymptotic formulas for things that weren't integer partitions and where you had to use this method and you couldn't use modular forms, which is how Hardy and Ramanujan did it. In the outside of the partitions context, this is called saddle point method. Okay, so I want to take the example of the number of involutions on n elements. So elements of the symmetric group that are just 2 cycles, products of 2 cycles. And yeah, let me call that I sub n. Then it has the following exponential generating function, which you can prove for homework if you want. So in this case, when you're dealing with labeled combinatorial objects, it's more convenient to have an n factorial down here. But the generating function is e to the q plus q squared over 2. All right, how much time do we have? Where should I go to? Till everyone's hungry? Okay, including me. All right, so there's our generating function. And first let's get the saddle point. Okay, well, I'm just going to do q times the logarithmic derivative equals n. So it'll be q times the derivative of the logarithm, that's pretty convenient, equals n. So we'll end up with q plus, what do we get here, q squared equals n. Quadratic formula gives you the saddle point. And obviously we're going to take the positive root. So this is what the quadratic formula gives you. Minus 1 plus root 4n plus 1. And I'm only going to need the, well, of course, you can plug this into the saddle point method, but it's annoying to plug this in. So let me approximate this. So I will just use, you got to remember your linear approximations in calculus. So this guy is approximately this. So just using that, I can get that this is approximately root n minus a half. Okay, because that's easier to work with than this whole nasty expression. All right, what else do we need to do? All right. So we have from Cauchy's integral formula, in divided by n factorial equals, so I'm just going to plug into this guy, the integral from minus a half to a half, and let me write this in the following way. I'll write this as e to the fq d theta, where f of q is everything that we need in the exponent. So q plus q squared over 2 minus n log q. All right. Now, thinking about how we want things to look on the major arc, I'm going to look at the Taylor expansion of this guy. Okay, so let's think about the Taylor expansion. Oh, and I should have said, we're taking q to have absolute value of the saddle point. So q is q naught, this guy. Yeah, I guess I should have said q naught is my approximation. So q naught times e to the 2 pi I theta. And we're going to trace our contour through q naught. Yeah, as we have. And I want to think about what this function looks like around Q naught. So f of Q is f of Q naught plus f prime Q naught Q minus Q naught plus f double prime Q naught. I'm just Taylor expanding like in calculus, plus f triple prime. Let me just say big O of f triple prime, like that. All right, I'm gonna rewrite this because I only want the things in terms of the angle theta. So pulling f of Q naught to the left-hand side is going to be convenient. And this is now f prime of Q naught. Factoring out a Q naught here. So e to the 2 pi I theta minus 1 plus f double prime Q naught squared over 2 e to the 2 pi I theta minus 1 squared. And then we have f triple prime okay, something like that. Let's see what time it is. All right. Okay, so for the major arc, I want it to look like e to the minus x squared. And well, before I go on, let's go ahead and evaluate these various f's, f prime, f double prime, f triple prime. Let's write down what these are. And maybe to save time, I'll just write down. Actually, I don't know. I think maybe it might be best to save this for next time since we have a lot to do still. But yeah, let me sketch what's going to happen, or just tell you in words. So what I want to happen is for, well, that to die and that to die on the major arc. And you're just going to have this. And that's going to look like a Gaussian integral that I can evaluate. And then the minor arcs you bound, and presto, you get your asymptotic formula. So we'll see next time how to complete that. Hopefully that gives you an idea of how to get started with this. And yeah, that'll do it. Let's go eat.